Hello. I'm admitting everyone in. I have to keep it clicking this button. Okay. More. Okay. Okay. Think everyone's in so far. Hello. Can everybody hear me? Oh, I have my speakers muted. Okay. Can everybody hear me?
Yes, sir.
Okay, good. Yeah, I actually have my speakers muted there for a minute, so I need to double check, make sure I'm okay. Everything seems okay. Let's see. No more waiting room. Okay. So, one person is waiting. How do I let them in? Oh, okay. I'm still letting people in. I thought I turned off the waiting room. I could have swore I turned it off yesterday. I probably turned it off in the other class and forgot to turn it off on this one. Okay, this waiting room is not working very well. Okay, one person's waiting. Okay, all right. So I'm gonna in a second I'm gonna switch to the desktop so we can start talking about frame buffers and pixels and things. But I'm just making sure right now that I've let everybody in first. There's another. Okay. All right. So anybody got a question? I mean, right now I'm waiting for people to show up. Does anybody have a question? Anything that's come up with the, say, with the what we talked about on Monday or on Tuesday or about the homework assignment? Nothing? Okay. Okay, I'm gonna go switch to the desktop now. I think everybody's been admitted. So I'm gonna share my desktop. Oh, mute. Okay. So here's the web page for today. What we're gonna do, okay, I got the video from last week, the other day up. So hopefully every day after class is over, I'll put the video from the lecture. If nothing goes wrong with it, I'll put the video from the lecture up on the. I'll replace this invite with the video for the lecture. Okay, and today we're going to talk more about pixels, frame buffers, and color. Pixels, color, and frame buffers. So we're going to do two things. I'm going to download these two zip files. We looked real quickly at this zip file the other day. This one's got little programs that let you watch pixels. And then here's some code and some pictures to help us understand pixels. So let me unzip those. Okay. Last night I looked around and I found a couple more pixel utilities. Still haven't found a really good zooming program, but found this one here that's new. I'll show you. We'll use it in a minute. It's got advantages over some of these other ones, but it's also not perfect. And also found another one. This one here. I didn't download it because it's a fairly large program, so I just put a link to it. It's an interest. I'll show you in a minute. Got an interesting take on zooming. It's a little bit designed differently, so it's got some advantages and disadvantages. Okay, so uh, so there's two new programs in here for looking at pixels, and it's funny. Oh, I have to admit somebody. Okay, I think that worked. All right, and then this other folder, okay, this folder has programs for zooming in on images and zooming in on pixels and see what they look like. And then this other folder is got it's just examples of the frame buffer. It's trying to help you get started with the first programming assignment. So there's whoops, I have to admit somebody else. Okay. So there's the frame buffer code in here, the frame buffer class, and a bunch of programs that make use of the frame buffer, meant to be examples of how you would program a frame buffer. So there's some example code of working here with a frame buffer. And then there's a bunch of images that we'll play around with. Okay, so first, remember, let me show you that everything you see on your screen is made up of what we call pixels. So like if I right click on my desktop here and I look at display settings, I'm told that my screen is, this is the pixel size. When they say display resolution, my screen is 1,920 pixels across this way. So that means my screen is a grid of 1,920 columns and 1,080 rows. So this is the width and this is the height. So this is how many columns of pixels there are, this is how many rows. You can think of it as a two-dimensional. We'll see it in terms of code, it's a 2D array. It's a 2D array of pixels. Okay, and you know, you can change this. I mean, I can set my desktop to a bunch of different resolutions, though usually you want to stick with the one that the recommended one is the one that your monitor is actually built with. My monitor here is built to have this many pixels, though I'm not even sure why Windows lets you do it, but you can downscale to different resolutions. Okay. All right. So the desktop itself is a 2D array of pixels. In the graphics card, there's a hardware frame buffer that holds all that data. So there's a bunch of data representing for every pixel on the screen what color that pixel is holding. And that data is held in a hardware frame buffer. It's actually a piece of memory. We're going to work mostly with software frame buffers. And I'll explain in a minute what we mean, but the computer has a hardware frame buffer in your graphics card. Okay, and in this case, the hardware frame buffer would be that size because it has to hold enough data to represent the color of every single pixel. Okay, and then if I go to this folder here of pixel utilities, you know, these programs let me zoom in and watch pixels. Like here's here's the one I like, but it's got a disadvantage. Okay, this one I think is in a way one of the nicest zooming programs. Okay, so here's where it shows you what you're zooming in on. It supposedly follows the mouse. Okay, so as the mouse is moving around, it's zooming in on a rectangle around the mouse. You can control how much it zooms by this. Like here's the maximum zoom. The maximum zoom is 32. So every pixel now is magnified 32 times. Now here you can actually see the pixels. You see how everything's made up of little squares. The little squares you see in that window are 32 times as big as they really are, but it kind of shows you that the screen is really, yeah, and by enlarging this window, I'm causing the program to enlarge more pixels. Right now I'm enlarging a letter, the letter O. Now I don't know where on the screen I am because the disadvantage of this program is that where the mouse pointer is not where the program is zooming. The program's confused. That's because this program is a little bit older. And what's happened is because of various reasons with changing software, modern computers have a feature, if you go here to display setting, of magnification. Your desktop is magnified, and that's messing up this program. Now, we saw this the other day. If I turn off the magnification, so let me just turn it off. Notice that everything in my screen shrunk. See, I turned off magnification. If I turn it back on, everything grows. If I turn it off, everything shrinks a little bit. Actually, real quick, by any chance, is Zoom being totally screwed up by this? Or are you seeing what I'm describing? Does it
No,
seem
it's following.
Because Zoom has weird problems sometimes with resolution. right? Does it? Do you see what I'm saying? That everything grows a little bit here, then everything shrinks a little bit here. Does everybody see that? Okay.
Yeah, I see it.
Okay. Now that there's no zooming by the Windows operating system, now this program is dead on. See, if I point at the little letter M there, M A G, see, the program is now dead on. Whatever I point to on the screen, that's what it's zooming. So that's what that letter C looks like. Okay. Notice that here's something quirky. What color is that letter Z? See see the word zip that is under here? What color is it?
Several colors, but it comes out black when it's not zoomed in.
It looks like it's black, but it's not really black. And we'll talk a little bit later on in the course, why in the world does a black letter actually be made up of lots of little colors? And that's a kind of quirky little thing. What you're seeing is something called ClearType. It's a trick. Everything you see on a computer is a lie. And I've mentioned this before in classes. Computers are unbelievably complicated devices, and everything you think you see is wrong. So you look at the letter Z, this letter ZIP, and everyone will tell you that they're black. And as a first approximation, yes, those letters are black, but in fact, they're not black. They're actually multiple colors, and you don't notice it until you zoom in on them quite a bit. Now, if I zoom out from them, like, okay, here now there's no zooming. Okay. And then if I zoom in a little bit, you still don't see the color. Now you can see that they're jagged. You can kind of start seeing the pixelness of the ZIP, but you don't see that there's colors there. It isn't until you zoom in quite a bit that you start realizing, wait a minute, there's weird colors there. Yeah. Why are there weird colors there? Yeah. And then you zoom in more, and you see that there's really colors there. Okay, like the I in the middle of zip is not black. Yeah, it's 3 pixels wide, and the pixels seem to be yellowish, brownish, and bluish. Yeah, the I is 3 pixels wide, but it looks like a yellowish, a brownish, and a bluish pixel. Okay, and if you zoom a little bit less, you can still see, yeah, it still sees 3 pixels wide, a yellowish, a brownish, and a bluish pixel. Okay, we'll see later in the course like why the pixels actually aren't the color you think they are when you look at them. Now, like these blue letters down here, notice that they're not quite 100% blue either. Yeah, you can see that they're multiple color too. Okay, see these pixels here. Now, sometimes when pixels look black, they really are black. Let me try something here. See, those black letters are really black letters. Okay, TextPad doesn't use the same kind of fonts as most Windows programs uses. TextPad is using an older kind of font, and these fonts, when they look black, they really are black. Okay, but notice that over here, the font is, see, that's a modern font. See, the hello is written in a modern font, and it's actually, it looks black, but it's really multicolored. But these over here are written in an older font. They look black and they really are black. And as you zoom around in TextPad, you see that in some places it's using more modern fonts. In some places it's using a more old-fashioned font. Okay. And if you play around, you'll notice that there's several different kinds of fonts, and you see the difference when you zoom in on them. Some of them are multicolored, some of them are solid color, and there's a third kind of font, which are grayscale fonts. They're kind of hard to find. Nobody uses them anymore. Either people use the real old black monotone fonts, or they use the modern, what are called clear type fonts. But every once in a while, you'll see something where the letters, instead of being shaded multiple colors, the letters are shaded in shades of gray. Probably won't find one here, but that's a third kind of font. It has to do with something called anti-aliasing. Okay, this is not an anti-alias font. This is an anti-alias font. Okay? So zooming is kind of neat. You start seeing things that you wouldn't even think is going on, that black is not black. Black can be all kinds of funny things. Okay. You start realizing that all kinds of funny things can be going on. Okay. All right. So we can zoom in and the computer screen is made up of little dots. Yeah. And here we see how each little dot is actually a little square. Those little squares are called pixels. And you color each pixel, and that's what draws things on the screen. Okay. By choosing the color of each, and that's what a renderer does. The software we're talking about in this course, it's the job of a renderer to color the pixels on the screen. These pixels are colored by what's called a font renderer. The font renderer picked those colors for those pixels to draw the words Erfranview. To write these letters, this was done using a font renderer. We're writing a graphics renderer whose job it is to draw 3D computer graphics. Most games use graphics renderers, but they actually switch to font renderers when they want to do things like 2D text. Okay, a renderer means a program that picks the color for every pixel on the screen. Okay, and you'll often see people use the phrase, I'm rendering the game, or I'm rendering a web page, and they mean that they're taking the data of a game and turning it into pixels on the screen. So we use the phrase rendering to mean picking a color for every pixel on the screen. Okay, now the whole screen is one big frame buffer sitting in the graphics card. Now every window here on the desktop notice that the window is a region of the frame buffer, but that window holds its own kind of data. A window in a frame buffer, we use the phrase viewport. So this would be a viewport in the desktop's frame buffer. And this is another viewport in the desktop's frame buffer. This is another viewport in the desktop's frame buffer. When you do the first homework assignment, you're going to use the idea of a viewport to draw. Actually, let me download the first homework assignment. In this image, you're going to see that this rectangle is going to be treated as a viewport. There's going to be a frame buffer that is this picture, but then there'll be in that frame buffer a viewport that holds that region of pixels, and another viewport that holds that region of pixels, another viewport that holds this region of pixels. Actually, this is two viewports side by side. Then there'll be a viewport that holds this here. Okay, so there'll be a viewport that holds this and a viewport that holds this, and they're kind of like mirror images of each other. That's not a viewport. And these squares, you could treat them as a viewport if you wanted to, or you don't have to. So viewport is a concept that sometimes makes it easier to work with graphics, though you don't always have to treat things as a viewport. But usually when you have a rectangular subregion of a frame buffer, it often helps to treat it as a viewport. So a viewport is a sub-rectangle of pixels in a frame buffer. The key idea is a viewport is this frame buffer has a coordinate system. The upper left-hand corner is coordinate 0, 0. Erfranview will even show me that. If I click on this picture, look over here where the title of the picture is, the title of the file is. When I click down, notice it changed XY 98101. That's the coordinates of where my mouse went down. If I go up here, 2, 2, I'm almost in the upper left-hand corner. If I go down here, notice that this is a 1000 by 600 pixel picture. And down here, I'm at coordinate 1000. Well, I'm at coordinate 997, 597. Okay. Like arrays, the upper left-hand corner is 0, 0. So the last pixel down here is 9,999, 599. I don't know if I can click on it. The last one is 999, 509. I'm not quite at the last one. Almost. There. Now I'm at the last pixel. Pixel X is 999, Y is 589. Okay. So now what about a viewport? When you create a viewport, you actually get a new coordinate system. If I think, well, if I think of this gray thing as a viewport, then this pixel has a coordinate of 737, 37 in the frame buffer, but it would have a different coordinate in the viewport. The viewport's got its own origin, right? See, that pixel there would be, it's pixel 728, 24 in the frame buffer, but it would be 0, 0 in the viewport. A viewport's a convenient new coordinate system. That's the advantage of a viewport. You can treat it as a new coordinate system and you can measure yourself relative to the upper left-hand corner of it. So once you anchor a viewport in a frame buffer, then you could work easily relative to the upper left-hand corner of the frame buffer. Okay, so that makes it easy, for example, to copy pixels from one region to another region. Okay, like if you have two frame buffers that are the same size, you can copy from one to the other, but just by scanning across this one and scanning down this one while you scan across this one and scan down this one. And you could use the same coordinates. 0, 0 here is 0, 0 here. 1, 1 here is mirrored by 1, 1 here. So frame buffers give you a sub-coordinate system. Now in Windows, that's the way this, now this window is a viewport to the desktop. But to the program EarthFran view, this window is its frame buffer. The program EarthFran view will treat this whole window as its frame buffer, and then it'll treat this image as a viewport in its frame buffer. Notice that this program, its frame buffer, like here, this program, its frame buffer would go from this corner down to this corner here. And then this program would have a viewport in it that was started up here and ended down here. And in that viewport, it drew what was in that file. This data file, this image file, is being copied by this program from that file into this viewport inside of its frame buffer. Then at some point, the Windows operating system communicates with this program, and the Windows operating system asks this program, what's in your frame buffer? Because I'm going to copy it to the desktop's viewport. Yeah. This program will hold these pixels in a frame buffer data structure, which is what we're working with like here. The program holds its data in a frame buffer data structure, and at some point, the operating system says to it, tell me what's in your frame buffer data structure, and I'll move it to the viewport in the hardware frame buffer that's owned by the graphics card. The operating system communicates with the graphics card. The operating system asks programs, what's in your software frame buffer, and I'll move it to the hardware viewport that represents your window. Okay, so there's one single hardware frame buffer sitting in the graphics card, and it's a frame buffer for the whole desktop. Every program running on Windows has a software frame buffer that represents its window. From the point of view of the Windows operating system, those frame buffers are really viewports in the desktop frame buffer. And at some point, the operating system asks every program to render itself. Tell the operating system what every one of its pixels are, and then the operating system copies those pixels to the viewport in the hardware frame buffer that's in the graphics card. Okay, and if you run multiple programs, each program, like right now, oh, here's a question. Does anybody know what program is this? What program owns that window?
Windows Explorer.
Yeah, it's the Windows Explorer program, which is part of the Windows operating system, but if I call up Task Manager, where's my copy of Task Manager? Okay. If I call up Task Manager and I go to the list of programs that are running, this program here, which is actually called the Explorer, that program is the program that owns that window. That Window's own, it's just another program. It's not actually, notice that this is not the operating system. The operating system does not own that window. The operating system owns the whole desktop. Every window you see on your desktop is owned by some program. None of them are actually owned by the operating system itself. And I think you've seen me do this before. If you kill that program, these windows just all disappear, and then you just get a blank desktop. But right now, it's this program that owns that window there. Okay, and this window is owned by the, where is it? Is it that one? I don't know if that's, I thought it was actually called Earthframe View. Maybe it's that one. Maybe iView. I guess, yeah, the process is probably, well, actually can find out. Yeah, that was, yeah. So the program, he calls himself iView. Okay, right? So there's the process that owns that window. What we call a window to the operating system, really can't remember, is a viewport for the desktop frame buffer. Okay, and the Windows operating system asks every process to let it know what are the color of all its pixels that are in its viewport. And then the operating system literally has to copy them from this process. The pixels have to be copied from this process into the graphics card. In the operating systems class, we call that inter-process communication. You have to, all of the pixel data is sitting in some data structure in this process's user space. And all those pixels have to be moved to the GPU by the operating system. Kind of like, it's just the same thing as if you wrote data to a file on the hard drive. Data goes to the file in the hard drive through the operating system. Here, data goes from a software frame buffer in memory of a process's memory to the hardware frame buffer in the GPU. And here we're going to see, here we wrote a software frame buffer in Java. This program is probably using a software frame buffer written in C++. Okay. And it's probably using a software frame buffer written by the Windows operating system. The Windows operating system has a library built into it that gives every program a software frame buffer. Java does too, but to make it easier for us to understand this course, I actually wrote my own frame buffer. The advantage here is that we can see the code, and I kind of tried to keep it simple. Java actually has a way for you to send data from an internal frame buffer to the operating system, but you can't see the code. Well, you can see the code if you're willing to go download the Java source code. I thought it'd be nice just to write a frame buffer data structure. Okay, so we'll look at the code in a little while, but that's a program that that's a program, that's a data structure that holds the pixel data. Okay, so it's just a data structure. This frame buffer does not know how to communicate with the operating system. So I kept this simple. This frame buffer does not know how to send its data to the operating system. In fact, the only thing this frame buffer knows how to do is save its data on the hard drive. Okay, so it can create these files. It can save its data to the hard drive. It cannot yet send its data to the operating system. We'll add that feature in another render. Okay, but so this is a really simple frame buffer. It's a software frame buffer, this file here, and it stores pixel data, but it does not know how to send that pixel data to the operating system. It only knows how, actually, if I open it, I'll show you. You go through the code, you get to a code down about towards the end, dump pixels. There's a method called dump pixels, which sends the data from the frame buffer to a file. That's the only thing it knows how to do. So you can fill this frame buffer and then save it. Later on, we'll see how this frame buffer could talk to the operating system and say, here's my pixel data. But right now, which is actually not that easy, it's not such a trivial thing to do. So right now, this is a very simple frame buffer. It only knows how to take its data and write it to the hard drive as a file. Okay, so, and it's not that much code to actually do that. The code to, all the code to write the pixel, to write the frame buffer to the file is right there. Okay, so there's the code that will dump. It dumps a, see the upper left, if you read this, UL stands for upper left-hand corner X coordinate, upper left-hand corner Y coordinate. That represents, you know, an upper left-hand corner of the frame buffer. Then a lower right-hand corner X and Y. So what it's doing is it's specifying the upper left-hand corner and the lower right-hand corner of what pixels to dump. So all the pixels between the upper left-hand corner and the lower right-hand corner, all those pixels will get dumped to a file. So that's the interface, okay? It dumps to a file all the pixels between an upper left-hand corner and a lower right-hand corner, right? Right, but it does not know yet how to send pixels to an operating system, okay? All right, now, so every program maintains its own frame buffer data structure, which is basically going to be a 2D array of pixels. And then most programs know how to send their pixel data to the hardware, to the operating system. I mean, our frame buffer is going to be at first kind of dumb. It only knows how to take its pixel data and send it to a hard drive. Most would know how to send this pixel data to the operating system. Okay.
But you said that every
Say again. Oh, you're breaking up.
Has its own frame buffer. What about programs that just run in the background? You said that every program has its own frame buffer. Right? What about programs that just run in the background that don't have any windows?
They don't. In fact, another thing that doesn't is a command line utility. Command line programs don't have a frame buffer attached to them. So that's a good point. Not every program has a frame buffer attached to it. So when a program starts up, it has to request a frame buffer from the operating system. So for example, my Java programs will create one of these frame buffer objects and then use it, but it can only save it to the hard drive. If you're writing a C++ program in Windows, your C++ program, like this one, when it starts up, would request from the operating system, it would instantiate a frame buffer object, but a Windows frame buffer object, and then it would fill it with data and send it to the operating system to be displayed. Command line programs wouldn't. They would not bother to create a frame buffer. So command line programs don't have, you know, like when you write a basic Java program in CS1, you just do standard in and standard out. You never do create a frame buffer object. The frame buffer object in Java is actually called a graphics object. So Java doesn't use the term frame buffer. They call them graphics objects. But when you create a graphics object in Java, you're creating a frame buffer. And then once you've created that graphics object, you can draw pixels in it. Okay, so we'll see a little bit of that code later on. So Java actually uses the phrase graphics object, not frame buffer object. Okay, so programs running in the background like services. See, there's all these services, you know, printer, like the printer driver and all that. None of those would have frame buffers attached to them. So a frame buffer is something that a program would request when it starts up. Just like we'll see in a little while that one of my graphics programs can instantiate this frame buffer object, fill it with data, and then save the result to the hard drive. A C++ program running on Windows can create a Windows frame buffer object, fill it with data, and then pass it along to the operating system and get it drawn on the desktop or saved on the hard drive. You know, a Windows program can take its frame buffer and write it to the hard drive. For example, this program can save, you know, it can save the image file to the hard drive if it wants. So it knows how to write pixel data to a file, but it also knows how to draw it on the screen. So yeah, not every Windows process, anything that's showing you a GUI, okay, like, okay, now this is actually kind of a quirk here. I just said that command line programs don't have a frame buffer. Then who's drawing this?
Command prompt.
Yeah, that your program actually has to communicate with CMD, and CMD has the frame buffer. And in fact, in Windows, it's even a little bit more complicated than that. Here's my command program, okay? Here's the CMD program. That program actually does not have the frame buffer. Now, if I write a GUI program, my GUI program would run inside CMD. CMD actually doesn't have a frame buffer. This guy does. This guy's called console host. If I close that CMD, notice that the console host didn't disappear quite yet. He stuck around. Okay, Windows didn't kill him. But the frame buffer is actually in the console host. Oh, I got another console host. Okay, so this CMD has that. Notice that, yeah, this CMD has console host 24044. Yeah, see, 24, this is another console host. This console host that belongs to somebody else. I'm not sure who on my Windows machine. But whenever you start a CMD, you get along with it a console host. That's the guy that owns the frame buffer. Okay, so the GUI, the command line program communicates with CMD. The CMD communicates with the console host, and the console host draws things on the screen. It's kind of a little bit messy. In fact, if you go back to an older version of Windows, the console host didn't exist. CMD had its own frame buffers. This was changed, I think, in Windows 7. I think it was Windows 7 that changed this. It used to be that CMD owned the frame buffer. Then Microsoft decided that wasn't really the best way to do things, so they created a separate thing to host the frame buffer. Then CMDs all live inside of console. They come in pairs now. CMDs live with a console host. Okay, and the CMD. Pardon me?
You have the same with PowerShell as well.
I think PowerShell does it the same way. If I start a PowerShell, notice I got another console host. See, now there's two. Now, where's the PowerShell? The PowerShell is
Usually towards the bottom.
Yeah, here's PowerShell. That PowerShell is, okay, you know, if you're in the operating systems class, remember the Task Manager is not really a great program for doing what we're doing. We should be using Process Explorer. Okay, let me, whoops. Trying to remember what folder I had Process Explorer in. Nope. See here, here's CMD. Anybody remember? What does that mean?
Child process.
Console host is a child process of CMD. Every time you launch a CMD, it launches a console host to host its frame buffer for it. Okay, and same with that PowerShell. Where's that PowerShell we started? Am I missing it? Does anybody see the PowerShell?
It's there. You're down just a little bit. You're right below it. Go up a couple.
Oh, there it is. See, there's the PowerShell. See how he created a console host underneath him as a child. When I started PowerShell, PowerShell started console host because in the Windows design, console host owns the frame buffer. So programs run in PowerShell, they communicate with PowerShell. PowerShell communicates with console host, and console host actually does the drawing of what you see over here. So so CMD and PowerShell don't even really have their own frame buffers. They have to live inside of. Now, the reason they did this, because suppose I want to log in remotely into a remote computer. So I'm running on this computer, and I decide I want to remotely log into a program somewhere else. So I do that with CMD. But the CMD on this program is not drawing on the other program. It's just communicating. CMDs really don't have to be drawing. CMD programs could be running without a GUI. It's usually done if one computer is communicating with another. There's actually no reason why a CMD has to have a GUI. That was their design decision. They came to the conclusion that CMDs, where did I lost it now? That CMDs actually are abstractions that don't need GUIs unless they're running on a desktop. So they separated the GUI part of the CMD from the CMD itself. So now on a desktop, a CMD starts up a console host, but when you're logging in remotely on another computer, the CMD wouldn't necessarily need a console host because it would need a GUI. The CMD running on this computer is talking to a CMD on another computer, and it's the other computer has to draw things on a desktop possibly. Okay, so let me close these. So notice there's a lot of interesting stuff going on. You know, we're trying to start getting an understanding of how things get drawn on a screen. You know, in this course we're going to start getting we're going to start building. It's actually an endlessly complicated thing, but we want to start getting used to the idea that you know, screens are made up of pixels. Every program is responsible for the pixels in its viewport, but this is a viewport to the desktop. It's a frame buffer to this program. Okay, so this program is responsible for the pixels in its frame buffer, but then the program has to transfer those pixels somehow to the operating system. Okay, all right. Now, remember, from our point of view, a frame buffer is a two-dimensional array of pixels. But what a pixel really is just a color. Okay, so when we say a pixel, what we really mean is a color, because all you really need to do is keep track of what color is at each one of the pixels. So if I blow this up a lot, what the frame buffer really does is keep track for, see, every little square on the left is a pixel. See, it's, you know, and every little square has a solid color. If you notice that you never have shading in these little squares, these, by definition, these little squares are the ultimate unit of a picture. So they're always going to be a solid color. No matter how much you blow them up, these little squares have to have a solid color in them. Okay? So there's a color. Now, a color in a computer is divided into an amount of red, green, and blue. So what a frame buffer stores for every ij, you know, for every, in the case of ERFRAM view uses XY coordinates. For every X, like right now, my mouse is at X coordinate 136, Y coordinate 52. That's that pixel in this viewport, the viewport that starts at this upper left-hand corner here. At that pixel in that viewport, notice that the RGB, now notice if you look up here, ERFRAM view tells me the XY coordinates of where I clicked, and it tells me the RGB color coordinates of where I picked. So there's the shade of red is 192. That's a shade of red between 0 and 255. We use 8 bits, which gives us 256 values for each color. So at that pixel, the value of red is 192, the value of green is 56, and the value of blue is 14. Notice that that pixel is reddish, because of the three numbers, red is by far the largest, 192 versus a maximum of 255. And blue is the smallest. So there's very little blue in that color and a little bit of green. Now over here, it's kind of yellowish. Well, what's yellowish? Yellowish is yellow is actually a mixture of red and green. So if you look at, this is a reddish yellow. Notice it's got a little bit more red than it has proportionate yellow. It's 250, it's 255 red, 189 green. So yellow is an even mixture of red and green. This is a reddish yellow, so it's got a little bit more red than green, and it's also got some blue thrown in. Okay, so it's got a little bit of blue. If I go down here, I get something that's much more bluish. Okay, notice that that's got a lot of blue, 230 out of a possible 255, and it's actually got a medium amount of red and green in it. So you get kind of an off blue. Here's something that looks pretty greenish. Okay, notice that the green is the largest of the numbers, but it's still got a fair amount of red and blue in it. Okay, so even though it looks predominantly greenish, that's the predominant shade in it, but it still has a fair amount of red and green in it. Okay, so you can go through here and you can see what the color of every pixel is. Okay, so the frame buffer data structure is a 2D array of RGB colors. So it's a 2D array of 3 bytes. Now, in this folder for, okay, one of the folders I downloaded from the website, this folder of code and examples. And it's got a text file in here called frame buffer versus data structure. So this is this idea that a frame buffer holds, it's a 2D array of bytes, and at every entry in the 2D array, there are 3 bytes. So here's how you could, this would be the C, C++, Java way of describing the basic concept of a frame buffer data structure. It's an M, that's how many rows there are, by N, that's how many columns there are in your frame buffer. It's an M by N array of 3 bytes, okay? And the 3 bytes are 1 byte for red, 1 byte for green, 1 byte for blue, okay? So that's your basic notion of what a frame buffer is, okay? Now, it turns out that in the real world of programming, not everybody this is what you might think of as, this is what's in the hardware. But we don't always do it that way in software. Like, here's a whole bunch of ways you could declare a frame buffer in software. Turns out that, and every program that manipulates frame buffers uses one of these, and every one of these is used by some program. There is no absolutely unified way to think about what a frame buffer is. This is what it is in hardware, but in software, for example, okay, here you could reflect it directly in software. You could say my frame buffer is declared to be an M by N by 3 array of bytes. But you could also do it as an M by N by 3 array of ints. If you do it that way, you waste a lot of space, because in every int, you store a number between 0 and 255. So you're using 32 bits to only hold 4 bytes, to only hold 8 bits. That's wasting space, but guess who does it that way? The Java language does it this way. The Java language actually, instead of using bytes when it stores frame buffers, it uses ints. Okay, you would think that that would be real wasteful of space. It is real wasteful of space, but there are advantages to it. It can be faster to process ints than bytes, because modern CPUs are word orientated, not byte orientated. So stepping through memory in bytes can be really slow. How do you get the second byte out of a word? See, a word is 32 bits. Okay, how do I get the second byte out of a word?
Don't you have to like shift it?
Yeah, you have to do a bunch of shifting operations. Okay, if you want to process memory this way, I mean, I see if if I had a chalkboard, I'd draw a picture at this point. Let me see if I can draw a picture to give you a sense of what's wrong with this. Memory, remember in the operating systems class, we said that memory is an array of bytes. So that's a byte, followed by a byte, followed by a byte, followed by a byte. Okay, but what's 4 bytes? That's one word. Then here's another byte. Here's another byte. Another byte. So far I've got, let's see, 1, 2, 3, 4, 5, 6, 7. Here's 2 words. Now the CPU holds registers. But what's in a register? A register is not 1 byte. A register is 4 bytes. So you have to grab 1, 2, 3, 4 bytes and move them as a unit into one register. But if this is RGB and you want the G, how do you get it? You have to grab, you can't grab the G. You have to grab RGB and this 4th byte, load them into a register, and then go find the byte you want out of that register. That's actually slow. Okay? Now in your graphics card's not talking to a GPU, a CPU. Your graphics card is different. But in the computer's main memory, having RGB, RGB, RGB in main memory is very messy because the CPU is loading 4 bytes at a time into a register, then 4 bytes at a time into a register. Trying to get the RGB out of this thing is a mess. Okay, so it's maybe better in a C or C++ program to have just waste some space and you put R here, wasted, 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 G, wasted, 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 B, wasted, 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 but then you could directly grab R, it would end up over here, and you would quickly, then you can manipulate the R, then you would grab the G, which would be the next word, and it would show up over, your bytes would always end up here in the register. And this could be very fast. So this could be way faster than this. You pay a price of wasting memory, but memory's cheap right now. Memory's dirt cheap right now. So speed would be more important. Okay. Now here's another thing you could do. You could do things this way. What this does is it treats this as an int, but instead of putting an R here, waste, 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 let me see if I can. The idea of this one is to pack the RGB into one int. So that would look like this. You put R there, G there, B there, this one's wasted. Then that is 1 pixel. Then when you grab that pixel, the R ends up over here, the G ends up over here, and the B ends up over here. And this one's wasted. Sometimes this is advantageous. Now, if you need the G, you still got to do some manipulating to get the G, because the G is in the middle of the word, and the B is over here. This has the advantage of not wasting too much space, but it still has the slight disadvantage. It's almost as if you were doing it's almost as if you were doing this, okay? But you just, it's putting RGB, waste 1 byte, RGB, waste 1 byte, but then you grab them as RGBs all at once, okay? So it's kind of another, it's actually more like this than it is like this. It puts the RGB into one word, and it's actually a fairly, because a lot of times you manipulate these RGBs together as a unit. Okay, so that's from a point of view of data typing. Oh, actually, here's the big difference. There's one big advantage this has over this. I pointed out that 4th one that's wasted is important. Can anybody see the trick? This packs RGB into 3 bytes. So the G is in the middle. So that's kind of bad. So does this. The G's in the middle. But does anybody see this one's got even a bigger problem? Does anybody see where the bigger problem comes? Give you a hint. It's the next pixel that causes problems. In this model, where's the next pixel?
Right after the B.
Right after the B. So how would you get the RGB for the next pixel?
You'd have to offset the previous pixel.
You'd have to actually read 2 words. Okay, so if this is an RGB, this R is in that byte of this word, but the G is in that byte of the next word. You'd have to actually read 2 words to get 1 pixel, because the pixels straddle, it's called non-aligned. This brings up the problem of non-aligned data. The pixels are no longer aligned on the CPU likes to grab things 4 bytes at a time. The CPU is in this case, I'm pretending it's a 32-bit CPU. It's grabbing 4 bytes all the time. It grabs 4 bytes, then grabs 4 bytes. That's what the hardware does. But if I do RGB with no wasted space, this R is in this word, but the G and B are in a different word. When I do this, what happens? Why is this actually better than this? Where's the next pixel? See how the next pixel, now what does that mean? I read 1 pixel in 1 memory access, and I get RGB wasted. Then when I want the next pixel, I do a very fast memory access and get the next RGB wasted. Okay. So this format can be read out of memory way faster than this format, because this format doesn't have the pixels aligned on words. The pixels they end up being RGB, RGB, RGB. They end up being non-aligned with words. But the key is that the CPU, you have to remember that the CPU only does things on words. How do I move this guy around? Can't I move this guy down? How do you move these things? Oh well. The CPU is hardware wired to read 4 bytes at a time. Now, if it's a 64-bit CPU, this is even worse. It's hardware wired to read 8 bytes at a time. Okay, it reads 8 bytes, then 8 bytes, then 8 bytes. And a 32-bit CPU reads 4 bytes, 4 bytes, 4 bytes. Colors are 3 bytes at a time. RGB, RGB, RGB. If you don't waste, if you don't, this is called padding. The technical word for this is padding. The RGB is padded with 1 wasted byte. RGB is padded with 1 wasted byte. That aligns the RGB with the word boundaries. That makes it faster. This does not align the RGBs with word boundaries. This one aligns the actual RGB individually on word boundaries, but it wastes a lot of space. So this wastes a lot of space. This wastes a little space. This wastes no space. It's way too slow. It's actually not used in any programming language. People almost never would write their frame buffers this way. The hardware frame buffer is this, but you wouldn't use this in software. Okay. Now, sometimes people model their frame buffers not using integers, but using floats. decimal numbers between 0 and 1. Now, when they do it that way, they always use a decimal number between 0 and 1. 0 meaning black, 1 meaning, well, if it's the red color, 0 meaning no red, 1 meaning bright. So what would be 0 as an int here becomes 0 as a float here. What's 255 as an int becomes 1.0 as a float. So your shades are between 0 and 1. A lot of libraries like to use floats for colors, not ints. Some even use doubles, okay? Now, Java has a color class, so you could create a 2D array of color objects. Now, here's the Java doc for the color class in Java. Notice that Java likes to use, remember I said some people use bytes, some people use ints, some people use floats, some people use doubles. Java picked floats. Okay.
Don't they also use that for the transparency and the,
Pardon me?
for the transparency, they also use it for that? There's
Yeah,
another-
that's the fourth. Now that extra byte that's I'm saying wasted here, it can be used for another purpose. It's sometimes called A for transparency. So sometimes they put here an A. Oh, what did I do there? Some libraries use the letter A here as a fourth byte, and it's called a transparency. And in Java, you could either use 3 floats or 4 floats. If you use a fourth float, it's called A. Well, later on in the course, we'll talk about what that transparency represents. It's, you know, we won't be using it for a while. So we're just going to emphasize the 3 colors, RGB. So Java uses 3 floats. Okay. It does 3 floats. It does not use 3 doubles. It also uses what we call packed int. It uses an int, notice it with RGB. You see? Okay. Now it also uses 3 ints. See? Notice that Java, since it's a class library, it actually lets you decide for yourself how you want to do it. So Java uses the 3 ints. It uses 3 floats. It uses the packed int. It does not use bytes. It does not use doubles. But in their library, when you construct a color object, you can give it 3 floats, 1 int, 3 ints, or 4 ints if you want. Okay. So notice I said that there's all these different ways of thinking about the structure of your frame buffer, and I say every one of these is used by somebody. Java actually chose to use 3 of them. You can design your frame buffer you can design your colors as 3 ints, a single int, or 3 floats. But Java does not accept 3 bytes, and Java does not accept 3 doubles. Okay, or you can just use a color object. You can think of it as a color object itself, because the ordinance here we're instantiating color objects. Okay. So in our code, let me go back now. What's in this frame buffer? The frame buffer is going to be an array of int. The pixel buffer is an array of ints. So I'm using, well, I'm using actually this one down here. Okay. Notice that these are all 2-dimensional arrays. You don't have to store your frame buffer as a 2-dimensional array. You can store it as a 1-dimensional array. These are 1-dimensional arrays, and that's what this is. Notice it's a 1-dimensional array of ints. The idea here is, let me draw another picture. here's my frame buffer. It's a grid. I'm going to try to draw. Okay, yeah, it's a grid of pixels. So I'm going to try real quickly, give you a grid of pixels. Okay, so frame buffer is a grid of pixels. It's a two-dimensional grid of pixels. It's got a certain number of rows and a certain number of columns. I can treat that as a two-dimensional array. So I can treat that as an array. I'll pretend it's an array int of size A and size B. Okay, so it's a two-dimensional array. Here's another way to think about this two-dimensional array. I can treat it as a very long one-dimensional array, where what I do is I put the first, I'll put the first row. So there's the first row. There's the first row. Then I'll put the second row in this one-dimensional array. Then the third row, then the fourth row. So this will be an array. This is an integer array of size int A times B. Big difference. Oh, shoot. This is an array int A times B. It's A rows of B columns. See, this is a two, notice the subtle difference. This is a two-dimensional array. It's got A rows of B columns. This has got one row, but the size of that row is A times B. This is the first row. This is the second row, third row. This is called a row major 2D array. Okay, it's called a row major. Well, you can actually, I don't know if you should call it a row major one-dimensional array or a row major two-dimensional array. It's a one-dimensional representation of a two-dimensional array in what's called row major form. Because there's another way to do it where you would have, you could also have it, Fortran does it this way. Fortran actually does the following. It has a one-dimensional array, but then it puts the first column, then the second column, then the third column. So the numbers from this column go first, then the numbers from this column go second, and then that kind of an array is called a column major array. Okay, so this would be column major. Fortran does it that way. Java and C almost never use column major arrays, but Fortran likes column major arrays. Java and C prefer row major arrays. So you think of first that row, then the next row. Okay, so your two-dimensional frame buffer can be represented as one-dimensional arrays. Now here it's a m by n by 3 array of bytes. Okay, here it's a m by n array of ints. So this is the row major version of this. And this one is the row major version of that. Okay, then there's a row major version of this, which is different than this one. This is the row major version of this one. Okay, the row major version of this one would be m times n times 3 ints. Notice that there's a lot of, you might ask, why doesn't everybody just do it one way? Why have 57 ways of doing something? And because none of these are, every one of them has advantages and disadvantages. Every one of these structures is good at some things and bad at other things. And depending on what kind of graphics library you're writing, you may prefer one of these over another one of them because of what kind of graphics library you're writing. Are you doing a 2D library that does font rendering? Are you writing a 3D library for games? Depending on what you're drawing, what your frame buffer is predominantly doing, you may actually decide different formats here. Okay, probably the most common, I think now, is this one. That's the one. Oh no, I'm sorry. is this one. I think the row major array is actually, oh, let me show you why. If you go back to this folder here, here's something cute. Okay. Where is it? See this? Here's a shortcut link to the Java Visualizer. Some of you have seen me use the Java Visualizer in class before. Watch this. This is really kind of nice. You know, that link links to a piece of code that I put up on the Java Visualizer. It's just 2 lines of code. It wants to show you the difference between a array in this format versus an array in the row major format. Okay, so it's showing you like what's the difference between actually using a 2D or a 3D array versus a row major array. Why would we prefer row major arrays? Okay, so visualize this. The beauty of the visualizer is it shows you the internal data. It shows you how Java lays something out. So what does this kind of an array look like in Java? That's what it looks like. What's it doing? You should, yeah, I hope you've seen this before in some, like your data structures class. What is going on here?
It looks like it's creating 3 4x5 arrays.
Yes, and it's creating, actually it's creating 4 5x3 arrays. Oh no, no, you're right. I'm sorry. No, you're right. You're right. It's creating 3. It's creating 3, 1, 2, 3. Oh, let's see. No, I'm sorry. It's creating, all right. It's creating 4 5x3 arrays. A points to a 4-dimensional array. So it's a 4A actually is a 4-dimensional array, a 1-dimensional array of size 4. A is a 1-dimensional array of size 4. So A is a 1-dimensional array of size 4. What's the first entry in that array? A 1-dimensional array of size 5 that each point to a 1-dimensional array of size 3. Does anybody see what's going on here? What can you tell me about the Java language? I created a 3-dimensional array, and this is what I get. What's that saying about the Java language?
It's way too complex.
Pardon me?
It's too complex.
No, okay, it is very complex. Programming is complex, but what does it decide to do? Okay, the answer is it now doesn't have anything. There's no such thing as a 2-dimensional array. There is no such thing as a 2-dimensional array. There is nothing like this.
So
Okay.
it's just arrays that point at other arrays, pretty much, right?
Yeah, that's how Java does it. Multi-dimensional arrays are all 1-dimensional arrays pointing at 1-dimensional arrays. Now, this creates a very complex structure in memory. This is way too slow. This is one of the disadvantages of the Java language, because you have no, these subarrays don't end up in the same cache line. So you don't have, they just end up in the heap scattered all over the place. Now, suppose you create this array, what we call the row major array. The row major array is just literally a 1-dimensional array contiguous in memory. It's fast. It's going to be all in one cache line. Okay, so we use these because they're actually way faster than these. These are easier to program. These are faster. In a lot of Java programs, you don't care about speed so much, so these are easier to program. You can think in terms of 3 dimensions. Here, you don't have 3 dimensions. You have to do your own array indexing. You'll see as we do go along, you have to do your own array indexing to get inside this array, but it's fast. In a graphics library where speed is important, you don't use multidimensional arrays, you use row major arrays, okay? So in a graphics library, you would not use a multidimensional array because C++ is a little bit more complicated than Java. In C++, you have you have a choice on how you want your multiple dimensional arrays to be stored. It is possible in C++ to have a multidimensional array that doesn't look like this, that looks more like this. Okay, but it's still got problems even in C++. So a lot of people in C++ will use a row major array. They'll just skip the multidimensional arrays altogether. Okay. So in Java, multidimensional arrays are way too slow, so people don't use them. And they're in a Java language, they're going to use one of these row major forms of representation of the two-dimensional array. So in the library we're using in this class, if you look at the source code to it, I had it up a minute ago. It uses the one-dimensional row major row of packed int. So it's using packed ints. Each int has an RGB and one wasted byte, which later will become part of the A for transparency. So it's using a row major one-dimensional array of packed ints. So we're using the row major one-dimensional array of packed ints. That's the one we're going to be using. That's the fastest from the point of view of Java to do this one. Okay. All right. Now we ran out of time, so I'm going to close some of this. Read for class next Tuesday. Start looking at the code in here. These examples here are good examples for you to get a sense of how to get started with the homework assignment. Oh, let me show you one last thing. See this file here says build and test the frame buffer. If you double click this, it compiles the frame buffer. And I built a main method into the frame buffer. So the frame buffer has a main method and it runs a test on itself. So the frame buffer generated all these images here. The reason I did that was if you go here and look at the frame buffer class, at the very bottom is a main method. It's a very good sense of how to program the frame buffer. This is a demo of how you should use the frame buffer. I wrote it as a test of the frame buffer. So every time I make any change to the frame buffer, I run this main method and it acts as the unit test of the frame buffer, but it also is a good demo of how to work with the frame buffer. So look for the lines of code here that generate each of these outputs. See the test 1, test 2, test 3. It's a lot of working with frame buffers and viewports. So read the main method and treat it as an example of how to work with a frame buffer. So remember I said in this course, one of the goals of this course is to get you to start getting used to saying, somebody dumps a bunch of code in your lap and just says, read this code, okay? And it's on purpose. Instead of saying, read this book, somebody just dumps a bunch of code on you and says, read the code, see what it does. You have to start learning from code, not learning from textbooks. So, you read the code and you ask questions and you Google things, but the source is the code. Read the code, learn from the code itself. This code makes use of this library, and also build the Java docs. Build the Java docs so you could read about the frame buffer library. So here's the Java doc to all the methods that are in the frame buffer. So you read the Java doc, you read the source code, read that main method, which shows you how to use it, and look at these examples here. They're pretty short. They're not long examples. See, they're just 20 lines of code each. But I think they do a good job of giving you a sense of how to work with a frame buffer. So read these examples. Okay. So on Thursday, no, I'm sorry, on Tuesday, we'll look more, again, we'll keep going, go through these examples in more detail. Okay. If you've got questions, just send me an email. We can always have a meeting by Zoom, or you can just ask questions by email. So if there's any kind of questions at all, please ask. I'll put the video of what we just talked about up on the course website. I'll try to save everything we did. And so we've gone over. So does anybody have any last minute question? While we're here, does anybody have a question? Okay. Okay, so I'm gonna, let's see, stop sharing. Okay, so I'll go ahead and end the meeting. And again, as I said, if you have any questions at all, please send me an email or request a meeting with Zoom. Okay, so I'm gonna end the meeting. Bye-bye, see you on Tuesday.